Lab 5, Choose Your Own Adventure. So for this, I chose to look at the wall of death, which is kind of when someone goes on a motorcycle on this vertical wall going in circles, and the only thing keeping up is essentially the force of static friction, and they need to maintain a minimum speed. So for this lab, the purpose is to model the circular motion of motorcycles on the wall of death and determine the minimum speed. To do this, we'll be looking at the momentum principle, curving motion, and then as a brief preview, it was found that the computer model effectively modeled the motion on the wall of death, that the minimum speed was found to be lower than that of actual real-life data because the computer model didn't consider drag forces. And in both cases, pretty close to, like the formula for the minimum speed was pretty close to the square root of the radius times g over the coefficient of static friction. So essentially, we'll just be looking at the momentum principle, and these are the main three forces. So the normal force acting perpendicular to the wall, the force of friction keeping the motorcycle up, and the force of gravity pulling it down. And the reason that we're doing this is because we're looking at circular motion. So the normal force is going to be mv squared over r, or in the perpendicular direction. And we're assuming that the motorcycle speed is constant, that there's no drag, and that we're treating in the system essentially as a point particle. So the system is a motorcycle and the motorcyclist, and the surroundings is like the wall and earth. So for initial positions, I looked at a video of the wall of death, and this is sort of what it was. It started at a fixed radius, certain height, but no z-coordinate. And the velocity is unknown, but that's something that I figured out using Tracker. So to do that, I just looked at the video, tracked the motion in the x and y direction, and then first found the speed by using the change in x over change in time. But then I also estimated the speed by just using the formula v equals 2 pi r over the period of rotation. So from this video that I used, the average speed from the data was around 8.47 meters per second, but for using the radius, which is probably more accurate because it doesn't have limitations like frame rate or the camera angle, the speed was around like 17 meters per second. Meanwhile, for the code to model this, I set the same initial conditions. I googled these two. So the motorcycle plus the motorcyclist mass is around 260 kilograms, and the coefficient of static friction is around 1/2, or 0.5 between rubber and wood. So then first, I set up all the forces as shown here, set the initial conditions, and then set the position and the velocity, and inside of this loop updated the velocity and updated the position. So really what I need to do is just to change the initial speed to figure out the minimum speed for the motorcycle. And so what I found is that at the speed 10.3, you have pretty much a perfectly circular first like orbit, I guess. If you go up any higher, than the motorcycle actually goes upwards. So this was a speed that made sense. And as you can see, the position x position oscillates, and so does the z position, like a sinusoidal graph, but then the y position kind of dips over time. So the minimum speed that we'll be using for the data is actually the higher number, which is probably more accurate. And for the computational model, it was this. And then also calculate a theoretical minimum speed by setting the centripetal force equals the normal force, and then solving for the minimum velocity. And that was found to be around 10.4 meters a second. So surprising how close the computer model was. And it's interesting to note that the minimum speed for the data was much higher than that. And so the reason that we're thinking that is because drag forces weren't considered. So air resistance, right? You would need a greater minimum speed to overcome that air resistance. And there's also an accurate physical context, an accuracy in Tracker. We treated the motorcycle as a point particle, which isn't the real case. And in the real wall of death, the wall isn't perfectly vertical. So let's talk about that. What if it was at a slight angle? Then you would actually need less speed because there would be this vertical component of normal force also keeping you upwards. So this is kind of what's graphed here. As you can see, if the angle is 0, then you get that speed that we calculated earlier. But otherwise, if you just keep on decreasing the angle, and the minimum speed goes down. Is it possible that perfectly vertical wall of death, which it technically is, but it'd be really difficult and dangerous because you have to go really fast, hope that the wheels don't slip, and the rider will have to control how they lean and move. So in conclusion, the computer model was pretty effective in modeling the wall, and then the data showed that the minimum speed was greater than the theoretical one, likely because of air resistance, and that tilt of the wall reduces the minimum speed required to prevent sliding down the wall. Thank you.